All right, today we are jumping into a concept that, let's be honest, sounds like it's straight out of a fantasy novel: imaginary numbers. But here's the twist. Despite that name, they are one of the most powerful, most fundamental tools we have for describing the real world. So, how on earth did a number that's supposedly imaginary become absolutely essential for everything from your smartphone to quantum mechanics? Well, let's get into it. Our story kicks off, like a lot of great math stories do, with a problem that just seemed completely impossible. It was a puzzle that, for hundreds of years, basically marked the edge of the map for what we thought was even knowable. It all boils down to this one simple-looking equation: x squared plus 1 equals 0. Now, if you just move the 1 over, you get x squared equals -1. So you're looking for a number x that, when you multiply it by itself, gives you -1. But just take a second and think about that. What number could possibly do that? And for the longest time, the official answer for mathematicians was, well, nothing. No solution exists. Think about it. Any real number you can imagine, whether it's positive or negative, it becomes positive when you square it, right? 2 times 2 is 4, and -2 times -2 is also 4. There was just no number on the entire number line that could solve this. It was a total dead end. But these annoying square roots of negative numbers, they just kept popping up where they weren't wanted. It started way back in the 16th century. Then, in 1637, René Descartes comes along and basically dismisses them with that unfortunate name we're stuck with today: imaginary. It took almost 200 more years before the legendary Carl Friedrich Gauss finally gave them a solid geometric home and made sense of it all. This was a really, really slow burn of an idea. So, you're faced with an unsolvable problem. What do you do? Well, if you're a mathematician, you do what you do best. You invent a solution. You just create a new number, a new rule, to break through the wall. And you can just feel the skepticism from the pioneers themselves. Girolamo Cardano, one of the first guys to really wrestle with these things, called them as subtle as they're useless. For him, they were just a weird mathematical fiction. You know, a trick you might have to use to get to a real answer, but they weren't real things on their own. And here is Descartes himself giving these numbers their name. You can just hear the dismissal in his voice. He's basically saying, yeah, sure, you can imagine a solution, but it doesn't actually exist. There's nothing real there. And that label, imaginary, it stuck. And boy, has it caused a lot of confusion ever since. So here's the big leap. Mathematicians just defined a new number. They called it I, the imaginary unit. And its one and only job, its whole identity, is that I squared equals -1. That's it. That one little rule changes everything. And when we combine it with the real numbers we already know, we get what's called a complex number, in that form a plus bi. It's got a real part, the a, and an imaginary part, the b. For the longest time, I just felt like a hack, a weird abstract trick. The massive breakthrough, the aha moment, didn't come from algebra at all. It came from geometry. It was about seeing numbers in a totally new way. Okay, so think about how we normally picture numbers. We use the number line, right? It's just this one flat, horizontal line that goes from -infinity to +infinity. Every real number has its own little spot on that line. It's one-dimensional. And this is the revolutionary question. What if there was another direction a number could go? What if numbers weren't just trapped on that single line? And this is the genius solution, the complex plane. It's the big reveal. All of a sudden, numbers weren't on a line anymore. They could exist anywhere in a two-dimensional space. The horizontal axis, that's our old friend, the real number line. But now we have a vertical axis, the imaginary axis. And a number like a plus bi is no longer some weird concept. It's just a point on a map with the coordinates a, b. It has a physical location. And with that single visual insight, all the mystery just starts to melt away. So now that we can actually see them, let's talk about what makes these numbers so ridiculously powerful. I mean, what problems do they really solve? It really all comes down to this monster of a theorem, the fundamental theorem of algebra. It's a guarantee, a promise, that any algebraic equation, like the one we started with, no matter how ridiculously complicated, finally has a solution, as long as you allow for complex numbers. All of those dead ends we kept hitting, gone. The world of numbers, in a way, becomes whole. And here's where your brain might start to bend a little. In this new complex plane, when you multiply two numbers, you're not just making things bigger or smaller. You are also rotating them. I'll say that again. Multiplication becomes rotation. You are literally scaling and spinning points around on this plane. And this one idea that a simple math operation is actually a physical rotation, that's the secret key that unlocks pretty much all of its real-world power. Okay, so they solve equations, and they can represent rotation. That's cool for mathematicians, but what does it actually mean for us? Well, it turns out this imaginary math is basically the foundation of our entire modern world. So every single time you stream a song, listen to the radio, or even just make a phone call, you are using complex numbers. A signal, like a sound wave or a radio wave, it oscillates. It goes up and down. And what is that? Well, it's a kind of rotation. And the perfect language for describing rotation is, you guessed it, complex numbers. They let engineers slice and dice those waves, filtering out the noise and giving us a clearer signal. The power grid that lights up your house runs on alternating current, or AC. That means the electricity is constantly flipping its direction, oscillating back and forth. Engineers use complex numbers to deal with this, to represent things like voltage and current in a way that makes the insanely complicated math of circuit design much, much simpler. They call it impedance. And now for what might be the most profound application of all. When you zoom way, way down to the deepest level of reality we know of, you get to quantum mechanics. And the basic equations that run that world, like the famous Schrödinger equation, they don't just use complex numbers. They are literally meaningless without them. It turns out these supposedly imaginary numbers are actually baked into the very fabric of the universe. And they're not just useful, they're also just incredibly beautiful. These infinitely complex patterns, like the famous Mandelbrot set fractal, are generated by repeating a very simple equation over and over again using complex numbers. It just goes to show there's this whole universe of breathtaking beauty hidden inside these simple mathematical rules. So, after all of that, we have to circle back to the name. If these numbers are so real, so fundamental, so useful, why on earth are we still calling them imaginary? I absolutely love this quote from Gauss. He's basically saying the whole mystery was just a branding problem. If from day one we had just called them something logical like lateral units, to describe moving sideways on that second axis, instead of something spooky like imaginary, nobody would have ever been confused. The name itself created the darkness. And that really leaves us with one final big thought. The story of imaginary numbers is really the story of an impossible problem that was only solved by daring to add a new dimension. It really makes you wonder, right? What problems that we think are impossible today are only impossible because we're stuck trying to solve them on a single straight line? What amazing breakthroughs are just sitting there waiting for someone to imagine a new direction?